You ever seen one of those massive offshore platforms and wonder how it all works? I mean, it's basically a floating city out in the middle of the ocean, dealing with some of the craziest conditions on the planet 24/7. So what's the secret? What keeps these incredible structures from failing? Well, it's a hidden world of engineering, all governed by a very specific, very important rulebook. Today, we're going to pull back that curtain.
So here's our game plan. We're going to take a tour through the circulatory system of a platform. We'll start with its hidden lifelines, the rules that hold it all together. Then we'll get into designing the perfect pipe, meet the gatekeepers, the valves that control everything, uncover the invisible enemies the system has to fight off every single day, and finally see how it's all built, tested, and proven to be rock solid.
Okay, so let's stick with that city analogy. If the platform is a city, then all its piping is the circulatory system. You've got these arteries and veins, right? And they're carrying incredibly volatile fluids under immense pressure. To make sure that whole system doesn't just, catastrophically fail, engineers have a critical rulebook they live by.
And this is it. It's called API RP14E. I know, it sounds super technical, but just think of it as the master blueprint. It's not about reinventing the wheel, it's a collection of proven, sound engineering practices that have been learned over decades. It guides every single decision from what kind of steel to use to how a tiny weld gets tested. Really, what this document is all about is preventing disaster by baking safety right into the design from the very first sketch.
All right, let's talk about the arteries themselves. You might think a pipe on a platform is just, well, a pipe, a simple metal tube, but nope. Choosing the right one is this high-stakes balancing act between material science, physics, and, of course, cost. It's way more complex than it looks.
So, one of the biggest puzzles to solve is just how fast you can move the fluid. You obviously want to move the oil and gas quickly enough to be efficient, but here's the catch. If you push it too fast, it can literally start to eat the pipe away from the inside out. It's a process called erosion. So, how do you find that perfect sweet spot?
Well, the answer often comes down to this number, 100. In the complex engineering formula that calculates the maximum safe fluid speed, this number, called C, is basically a universal speed limit. It's a conservative, proven constant that helps designers find that exact point, the top velocity a fluid can hit before it starts to wear away the pipe. It's what ensures the system can run safely, day in and day out, for years and years.
And this just shows you that even picking the type of steel pipe is a huge decision. The two most common ones you'll see are ASTM A106 and API 5L. Now, A106 is only made as a seamless pipe, meaning it's one solid, continuous piece of steel. That's usually preferred because, well, there's no welded seam, which means there's no potential weak point. It's got consistent strength all around. API 5L, on the other hand, can be either seamless or welded, which gives you more options. But if you go with a welded version, you better believe it requires some seriously strict quality control to make sure that weld is absolutely perfect.
So, if the pipes are the arteries, what are the valves? They're the heart valves. They're the absolute gatekeepers of the entire system. Their job is to start, stop, and control the flow of all that power, and they have to do it with incredible precision. Without them, the whole thing is just a runaway train.
And just like pipes, not all valves are created equal. You have to pick the right one for the right job, and that means making trade-offs. Take a look here. A ball valve is all about speed. You give it a simple quarter turn and bam, the flow stops instantly. A gate valve, though, is built for strength. It's slower, sure, but it's designed to create a super tight seal in really high-pressure situations. And notice the limitation on both? A big no-no is trying to use them to throttle or finely adjust the flow. They're not designed for that, and doing it can wreck their internal sealing surfaces in no time.
So, if you boil it all down, valves really have three main jobs. The first is that simple on-off function we just saw. The second is throttling. For that, you need a different type of valve, like a globe valve. Think of it just like the faucet on your sink, where you're precisely controlling how much water comes out. And the third job is the check function. A check valve is basically a one-way door. It lets fluid pass through in one direction, but if that fluid tries to flow backward, it slams shut automatically. Super important for safety.
Now, no matter how perfectly you design a piping system, it's immediately in a constant battle. A battle against invisible enemies that are trying to break it down from the inside out. It's a never-ending war against decay.
Just look at these numbers. They're pulled straight from that API standard. They really show you how sensitive steel can be. If the salt water, or brine, that's often mixed with oil and gas, contains more than just 0.025 parts per million of oxygen, it becomes corrosive. I mean, that is an incredibly tiny amount. For CO2, the threshold is higher, but the idea is the same. These tiny, seemingly insignificant contaminants can launch a full-on attack against the integrity of the system.
And then you have one of the scariest enemies of all, sulfide stress cracking. This is not your garden variety rust. This happens when you get hydrogen sulfide gas. That's the stuff that smells like rotten eggs, and it mixes with water. Under the right stress conditions, it can attack certain metals and cause them to just crack and fail, catastrophically. But you know what the truly terrifying part is? It can happen with absolutely no visible warning signs. The pipe doesn't get thinner, you don't see any metal loss, it just breaks. And that is why the standards are so unbelievably strict about material selection and hardness. So you've made all the right design choices. You've picked the perfect pipe, the right valves for the job, the best materials to fight off those invisible enemies. Now what? Well, the whole system has to run one final crucial gauntlet. It has to be built, tested, and proven to be absolutely sound before it ever sees a single drop of oil or gas.
This is what that path to integrity looks like. First, you have to qualify a welding procedure. Think of it like creating the perfect recipe for joining two pieces of pipe together. Step 2, you have to qualify the welder themselves. They have to prove that they can follow that recipe perfectly, every single time. Third, you X-ray a certain percentage of the finished welds. This lets you see inside the metal to find any hidden flaws that you'd never catch with a visual check. And finally, the whole thing gets put to the ultimate test. The entire system is filled with water and pressurized to way, way above its normal operating pressure. If it can hold that pressure without leaking or failing, then, and only then, is it proven ready for service.
You know, when you look at an offshore platform, what you see is a marvel of steel and machinery. But what's really holding it all together is this massive, unseen effort of engineering, guided by these detailed rulebooks like API RP14E. It's really a testament to planning, precision, and learning from the past. And it kind of makes you wonder, doesn't it? What other invisible standards, these hidden rulebooks of engineering, are out there quietly keeping our whole modern world from falling apart?